Okay.
Okay, continue. Sorry.
Okay. So just giving a background, as I had said, my research is on impact of agricultural activities on water quality, stream flow, and there are various benefits we get from agricultural activities such as irrigation. But on the flip side, we have a lot of non-point source pollution and movement of the water quality materials. So there are a lot of effects of these agricultural activities, and their extent are not well understood due to the spatial and temporal variability. But using hydrological models or mathematical tools, we can be able to try and estimate some of these processes and understand how we can predict them into the future and get some more in-depth knowledge about them. So in this presentation, I'll do two things. So it's about how we evaluated our SWAT model that we used for the climate change impact analysis for two emission scenarios, that is RCP 4.5 and 8.5. So my study area is called Sidakos River Watershed. So it's a kind of a sub-basin. So it's located in northern Spain in a place called Navarra, and it's about approximately 500 or 480 square kilometers. It's part of the larger Ebro River Basin in Spain. Within the basin, it's both irrigated in the south, about 16%, and the majority of it, the northern part, is highly rain-fed. So our simulation was mainly based on the rain-fed area. We didn't focus on the irrigated part for our modeling purposes. So, and the altitude again varies. The lower side is very, very low at 300, so it's a spatial variability, and mountainous in the northern side. Climate is Mediterranean. Rainfall also varies. The high altitude have higher rainfall of close to 1,000, and low altitude has less than 500. And so the model of choice was the SWAT model from the United States Department of Agriculture. I think most of us already know about the models, a semi-distributed model, both physically and process-based. Operates mainly on a continuous time scale, although there is the sub-hourly, but it's rarely used or even recommended for those who are not advanced modelers using it. So most research you'll find on the daily time step. And it uses the water balance equation to perform the hydrologic cycle simulation. So for the setup of our model, we had the digital elevation map for the topography, and then we had the land use map with various land uses. Here I have just given the overview of the land uses as they are, but when I was using them in the model, I subdivided them based on the different crops that are mainly grown. So whether it was under the non-irrigated area, specific crop that they put in each parcel of land, and also for the entire area. And then the land use are based on the FAO land uses. So for this area, we had about 8 or so. Not land use, but the soil use are based on the FAO soil classifications. And this also helped us to generate the user soil from the FAO map that we used. And overlaying these 3 maps, we were able to generate about 1,400 hydrological response units and about 23 subbasins, which were used for our simulation purposes. So in terms of the main inputs, we have the spatial data, the ones I've shown, the DEM, the land use, the soil map. And then we have the weather data. So I used climate data, daily climate data from 1990 to 2000, but the simulation was done from 2020, but simulation I did from 2000 to 2020. So 10 years I used like a warm-up period for my study. And then I had also the agricultural management data, which included the cropping cycle, the rotations, the fertilization, the amount of irrigation, what applied. And then for the climate change, I did two simulations. So I did one simulation for the historical climate from 1971 to 2000, and then I did the future projection from 2011 up to 2100. And my climate change was divided into four main categories. So I used the baseline or the reference historical data as the baseline that I used for comparing with the future projections. So the future projection, I divided them into short term, which I divided into 30 years periods. So the short term was from 2011 to 2040, and then the medium term from 2041 to 2070, and then the long term projection from 2071 to 2100. So to calibrate or to simulate climate change using the SWAT model, okay, the process is about once you have calibrated your model and obtained you presume it's the best with the best parameters, then you change your climate data. So you just change the two main climate data, which is always the precipitation and temperature for whether it's the future, whether it's historical. So you change them, and then you just change those files in your SWAT model, and then you also adjust the carbon dioxide concentration. So if you have general idea, you can put that range. If you don't, then you just put, like for me, I didn't know much, so I just put the entire range from, usually it's average like 400, but I just put the entire range from 0 to 1,000, and then the model will pick the best carbon dioxide concentration based on the input data. And then you do the number of iterations with the parameters that you had set. You do a similar number of iterations as during the calibration. So mine, I did 500 iterations, and then I extract the variables using the no observation in SWOT-CAP. So in terms of my results for the stream flow, was a bit good when doing the calibration, the pattern and even the peaks were quite captured well with the slightly for more than 0.8, which was very good for our case. Usually anything above 0.7 is considered satisfactory and okay. And among those parameters that we identified as sensitive for the stream flow calibration were the curve number, which influences the flow of the runoff. And then this area being Mediterranean, there is very high evapotranspiration. So we also had the soil evaporation compensation factor. And then the groundwater parameters were also highly sensitive for our area. And I'm not so sure, maybe two reasons, because the soil maps that we used were a bit coarse, and so I don't know whether it was contributing to this sensitivity. And also this area is more sandy loam region, so a lot of infiltration also. So those sensitivity now are groundwater, like the available soil water capacity, the groundwater delay time, and also the base flow factors were highly sensitive in our model. For nitrate, again, the model was somehow okay for us, although during the validation it was a bit lower than the calibration, and this maybe could have been because of a lot of data, missing data in the nitrate concentration, which we changed to nitrate loads that we used. And there was some time that there are data that were not being collected in some months. So we used in our watershed, the nitrate concentration is collected through the manual, like grab sampling, but it's done only once per month. And so some months they also skip, and it's not like a specific day. You find some months they do the collection at the beginning, some at the end, some in between. So it's quite random. And so we just assume that this 1 month data is representative of the entire year. So there were high uncertainties with that. But since it's highly correlated to the stream flow, so because we were using the loads, so we kind of found reasonable evaluation for it. And also the sensitive parameters are as shown there. So for the climate change, in terms of the inputs, we have a general decline in precipitation from the short term to the medium term as you go to the long term compared to the base for all the models, or for all the 6 models that we used. And the temperature is increasing, and this is in line with the prediction of the IPCC projections of the Mediterranean region, where rainfall is expected to reduce, while temperature is really expected to increase from up to about 4 degrees, average 4, but some can be as high as almost 6 in in this area. So a summary of the climate inputs are the precipitation declined by about 5% in the midterm, by about almost 7 to 10%, and almost 15% for the RCP 8.5 in the long-term projection. My temperature was increasing from about 1 degree to about 5 degrees or so. Yeah. So in terms of now the outputs that we got, the stream flow showed a general decline, and with a higher decline in the RCP 8.5, especially in the long-term scenario, where we could see in the inputs also the temperature was increasing so much, and the precipitation declining a lot. So again, that resulted into the much decline into for the RCP 8.5. The RCP 4.5, because there are intervention measures that are being put in place after around 2050, it showed almost similar declining patterns between the short term, between the medium term and the long term. So it didn't have tremendous decline. And that is also reflected with the inputs that we had there. So we just thought this increase was mainly due to increased evapotranspiration because of increasing temperatures that will be experienced in this area. And then for the nitrate, the pattern was almost the same, because the nitrate loads are highly dependent on the stream flow. So a decline in stream flow definitely results into a decline in the loads. However, when we look at this, we also look at it from the point of the concentration. The nitrate concentration are expected to rise, to increase, because there is very low amount of water that will dilute them. And so that we see as a potential negative effect that will in this area, if everything. So the patterns are almost the same, and this just because of that. And seasonally, the most affected season we saw was just after summer. So summer and autumn had the highest decline in precipitation, And decline in nitrates or the nitrate concentration impact varied from season to season, so we cannot pinpoint any season that we say, okay, this was the highest, but we can see some of the long term is highly affected. So in conclusion, we can conclude that the SWAT was able to simulate stream flow and nitrate load for our study area quite well, and the general decline in stream flow and nitrate load, especially the long-term scenario. While stream flow decline was highest in Atum, and the nitrate varied for each scenario differently. And the main climate change driver here is probably the temperature, although the rainfall also counts, but we think it's temperature causing increased evapotranspiration. So thank you for that.
Thank you. It was very interesting.
And a very nice presentation. Yes.
So any question, feedback, comments are highly welcome. Can help me also improve on the manuscript I'm currently preparing. In terms of more discussion that I can have. Yeah.
I think Farouk raised his hand, so maybe he can ask.
Yeah, hey, hello. Thank you, Brian. Very good presentation. Have you taken into account possible changes in yields for these future scenarios, or how did you handle the crop yields?
Okay, I did not specifically take into account the possible changes in crop yield, but what I did is that we used for the future projection, we used the heat units to project how the harvesting, the planting, and so on will happen, so that the model just determines depending on how much, because we presume that in the future, because it will be a lot, the temperatures will be higher, probably the periods with these plants will take to grow until harvesting will become shorter. And so with heat units, it can automatically determine, but we did not have any other method that we specifically put to determine this.
Okay, I'm asking just because the yields would really affect the nitrogen concentrations. So if the yields are assumed to be lower, then you probably have a much higher losses of nitrogen. So that's something you may just discuss in your manuscript. What would be the consequences, whatever the yields ends to be in the future scenarios.
Yeah, for sure. I'll keep that in mind.
I was wondering because you said you used 6 different like circulation models for future climate. Did you use all of them to test, and then like were there significant differences between the outcomes of those, or did you kind of use the mean outcome of those models? Yeah, I was just wondering about that.
Yeah, for the analysis, the general analysis, I used the mean, the overall mean of them. But I did run each of them for each of the 6 of them, both for the historical and the future for both RCP 4.5 and RCP 8.5. So in total, I did about I think I did 18 simulations of 500 runs each, but I didn't go into checking whether how significant the outputs are amongst each other. What we did was, okay, we only gave the band that this band that shows for which the highest and the lowest, so between the highest and the lowest, yeah. So
Yeah.
it kind of like provides an uncertainty range of those outputs, yeah.
Yeah. So there seems to be like some variance, but it seems that they're like all kind of behaving in a similar way at least, or
Yes.
yeah, or responding to the same way.
Yeah.
Could you tell us a bit more about what were the sensitive parameters for the nitrate loads? Because I didn't manage to read it when you were.
Okay, the nitrate loads were mainly affected by the denitrification exponential rate. I think this affects how much the denitrification happens, and then the fraction of porosity of which an ion excels. So how much the nitrates get attached to the soils and the pore spaces in between them, and then the fixation, the nitrogen fixation, and this is usually more when you have leguminous crops which do nitrogen fixation, so like beans, peas, and so on. And then the intake, nitrogen intake uptake distribution parameter, and the concentration in groundwater. So those were some of the key parameters there.
I was very impressed with your Nash static efficiencies. In Inca, that I have been working with, the Inca P phosphorus, then if you have over like 0.3, it's fantastic. Like you would get a higher efficiency than that. So,
For phosphorus?
yeah.
Yeah, phosphorus, of course, phosphorus is always a bit challenging because we always look at it in three times. So you have to have your stream flow right, and then it's dependent on, after you get your stream flow, you look at the sediments, and sediments is always very difficult to get right, and then phosphorus is dependent on the sediments. So you find it's always a bit challenging, and even most hydrological studies always recommend, like for SWAT, they always recommend anything above 0.4 for phosphorus.
Okay.
And but nitrate is only dependent on stream flow, and
Yeah.
it's always recommended about 0.6
Yeah.
and above for that.
Yeah.
And stream flow 0.7 almost. Yeah.
But it's really nice that you can capture all of those dynamics.
But isn't Inca calibrated towards the concentration? And here it's calibrated to the loads.
You can choose, I think, in SWAT too, or that's what they say.
No, it has the component, but it always gives a zero output. I don't know why, but the output in SWAT has the concentration, but I've never seen it bring it out. And it's also, they say it's not advisable to calibrate using concentrations. If probably it can, which I've never seen it bringing mine. I saw just that column bringing 0, 0, 0. I tried asking why, and they said no one uses it. So I think it's a setup thing in the SWAT model. So they have just put it for the sake of it, but you don't get anything. So
Because
so
the
it's better
people
use load. Yeah.
that I'm working with in this EU project, they are talking about calibrating to concentration. Since if you calibrate to the load, it's very biased by the flow.
Yeah.
So then you will get a nice relationship, regardless of the fit of the concentration.
I guess it also depends what your aim is. If your aim is to
Yeah.
improve local water quality, then concentration is definitely important. If you aim to kind of discuss or investigate the exports to other systems, then I guess loads are more relevant to be correct, I guess. But yeah, in high,
I think
yeah.
We have to leave the room now. It's booked. There are other people outside here.
Ah, really?
I think
Okay.
it's been double booked probably.
Okay.
But we booked
Okay.
an hour. Did you?
Yeah, but it says here also that they're booked from
Ah,
2.
okay.
Oh, okay. I thought it was booked for an hour, but that's unfortunate.
Yeah. It might have
Um,
been some kind of.
But maybe we can find another room for this
Yeah.
session.
Yeah, we could also
Yeah.
move to another room if
Yeah.
we keep the Zoom link open.
yeah, we'll keep on Zoom. I'm sorry.
Yeah, we'll move to another room. Yeah, or at least. Yeah, maybe and call here maybe at least.